Hey viewers, Thrasher here. This video is conservation of energy, a very well-known topic in physics. It encapsulates what we've been doing in the last kind of 4 videos within this E-dot sequence, and I want to show you where this idea comes from and how to apply it to problems, okay? So to start, I have up here at the top a very broad-seeming sentence. It says, let's look at all the work that can be done on an object. And I literally mean that. I don't have a diagram or anything. I want to keep this as broad and as general as possible because that actually means our conclusion, our result, is very broad. It's very powerful because it can be used as long as we are analyzing the work done on an object. And I could put on any object right here. Okay, so what does that mean? If I'm looking at all the work that can be done on an object, well, that must mean I'm looking at the net work, right? That's what all the work means. I'm looking at the net work done on an object. You know, if there's one force doing work, it would just be that single force. If there were 20 forces doing work, it would be all 20, and I'd probably add them all up. So whatever it is, very generally, it's the net, it's the total. Just like, you know, looking at all the forces on an object, adding them, subtracting them, that's looking at the net force with the second law. Okay, so I'm going to look at the net work on an object. Well, you know, we learned that there were 2 types of forces. There were forces that are called conservative and forces that are non-conservative. Those are 2 very broad categories. Remember, work is always about forces, so the total amount of work, well, I could look at that as the 2 different categories. That would be the work done by all the conservative types of forces, as well as all the work done by the non-conservative forces. I'm not making any claim about whether there's 1 or 2 or 3 or 12, or here if there's 1 or 20 or 1,000. But, you know, if I'm looking at all the work and there's 2 categories that are possible for the types of work, the work done by conservative and the work done by non-conservatives, this equation is valid. Okay. Well, what could my next step be? Let's imagine scenarios where there's no non-conservative forces. I'm going to cross this out. If you remember from the last video, a lot of forces are actually non-conservative, especially things like frictional forces or kicking forces or punching forces. A lot of forces that get in the way, they have non-conservative attributes. They can't be undone. So let's say we're going to ignore that. We'll ignore all these non-conservative forces doing work. So what does that mean I'm left with? I'm left with the net work is equal to the work done by conservative forces. Okay. And what are the only types of forces we've learned that are conservative? Well, in this class so far, we've only learned of one, the weight, or you could say there should be an H and a T right there, the force of gravity. So we're only going to consider the work done by the force of gravity. That doesn't mean there's no other forces. There could be other forces, just there's no other work being done by those forces, okay? So we're just going to focus on what types of forces? The forces that could be doing conservative work, and that's the force due to gravity that we've learned so far. Okay, we also learned something about the net work. By the work energy theorem, what is the net work equal to? It's 1/2 mv squared minus 1/2 mv naught squared. Okay, and that's going to be equal to the work done by gravity. I learned that that was equal to mg h naught minus h. Okay, remember, the reason why it's not h minus h naught is because I need this work to be positive. I talked about it in the last video. You could check that out. But this is valid. This is an okay way to write this. And let's write that as mg. I'm just going to factor, I'm just going to distribute mg h naught minus mg h. Okay, well, interesting. On the left-hand side, I have this term for kinetic energy after minus the kinetic energy of an object before. And then on the right-hand side, I have a gravitational potential energy before, with this little naught symbol, minus a gravitational potential energy after. Just for the sake of clarity, let's maybe put all these things in the same time on the same location. What I mean by that, I'm going to swing this mg naught, or this mgh, over here, so it's with this 1/2 mv squared, this final kinetic energy and this final gravitational potential. And I'm going to swing this mgh naught, I'm going to actually leave that here and swing this one over here on this side. So it's on the same side of the equation. So I'm going to be left with 1/2 mv squared. Ooh, I'm adding this, so plus mgh. That's going to be equal to mgh naught plus, because this is minus right here, so I'm going to add it to the other side, plus 1/2 mv naught squared. And man, this is pretty interesting looking. On this left-hand side of the equation, we learned this type of kinetic energy before. We know that this is a gravitational potential energy. And there's no not symbol. This is the values of these at some later point. These are the only two energies I've learned. I could write it like this. This is the energy at some later point, just some E. And over here on the right-hand side, I have the gravitational potential energy in the beginning at some starting height. I have the kinetic energy in the beginning at some starting velocity. I could say that's equal to E naught. Oh, notice what I have. In total, the total energy after some motion, after some time, is equivalent to the total energy beforehand. The final total energy is equal to the initial total energy. Oh, this means that the total energy is staying constant, or put another way, the total energy of this object, total E, is conserved. Conserved is a fancy word meaning it's staying constant. This is what we mean by conservation of energy, this right here. The total energy, and this equation right here, the total energy is staying the same. Now remember, there was a big caveat, and I have it at the top. This is important to recognize. This was true, the total energy remains constant as long as there were no non-conservative forces, no friction getting in the way, nobody punching the ball when it was flying through the air, nobody slapping the block off of the ramp. But as long as there are no non-conservative forces, the total energy is the same before and after. Okay, this is conservation of energy. It comes from us understanding conservative and non-conservative forces, as well as us understanding the work energy theorem. Well, okay, that's maybe broad, but remember, it was broad on purpose, because I can apply this to any scenario. Let's see what that means. Here's an example that we've actually might have looked at in the past unit. We have an object on an incline. Now, I'm telling you that this object on an incline is starting at rest, so V naught is equal to 0. Now, let's say when I release it, there's no friction, so that's important. So when I let it go, it's going to start going down, and then down, and then down, maybe picking up speed. That's probably a fair guess. Let's say I wanted to know the velocity at the end. How would I have done that traditionally? Well, maybe I would do like a free body diagram, right? Maybe I'd do mg here. Okay, maybe I'll look at the normal force. Maybe I'd break this into components like this. Maybe I do the sum of the forces in the x direction, some of the forces in the y. I'd find some acceleration. Maybe I'd use some constant acceleration equation. Oh my gosh, we're going to see that none of this is actually going to be necessary. Let's try using this idea of energy conservation. If there's no non-conservative forces, there's no friction. Okay, there are other forces on the block besides weight. There's the normal force, but that's not doing any work because it's perpendicular. So if there's no non-conservative forces, I can say this energy in the beginning is in fact equal to this energy at the end. So, okay, what are all the possible types of energy it could have in the beginning? Maybe it has some kinetic energy. Let's just write out just kind of nice and big, a very broad general equation. Equals 1/2 mv squared plus mgh. I'm going to kind of compact this side on the right just because I know my screen is right here. Okay? All right, so here's my broad equation. The initial energy should equal the final energy. In the beginning, measured from this location here, let's call this h equals 0, just so we're on the same page. Well, the block is some height above the ground, but does it have a velocity? No, it says v naught is 0. This whole term goes away. So on the left-hand side, I just have mgh naught. Now, I'm not going to break anything into components. Remember, h was just the vertical distance. M is the mass, and g is just 9.8. Okay? So I have here nothing that has to get broken down, just mgh naught. Now, over here on the right-hand side, is there any more gravitational potential energy? There isn't. Because at this location, the height is equal to 0, right? I was measuring from this location. So there's no more gravitational potential energy. So, is there kinetic energy? Yeah, it's probably moving, right? The box is probably moving at the bottom, so I have 1/2 mv squared. I don't break velocity into components. This is a scalar. Nothing needs to get broken down. This is my equation. Can I do a little more simplification? You betcha. The mass cancels out if I divided both sides by mass. If I multiplied both sides by 2, so I got rid of this half, I would have 2 times g times h naught equals v squared. Or v, if I take the square root of both sides, v is equal to the square root of 2 times g times that starting height. And oh my gosh, I could solve for this final velocity without having to break things into components, without having to draw free body diagrams, without having to use a constant acceleration equation. If I recognize that the energy is the same before and after, if I can write that out, and then I use my noggin, and I think, okay, let's see, is there any kinetic energy in the beginning? Yes or no? If no, the whole term drops out. Okay, in the end, is there any gravitational potential energy? No, because there's no height. That whole term drops out. Okay, in the end, is there kinetic energy? Yeah, because it's moving. I can use this kind of big original equation, but things simplify. Look at this, real quick in my calculator, the square root of 2 times 9.8 times that starting height. That would give me the velocity. Now, it doesn't matter whether the box is on a flat section or down a ramp. It would be the velocity in that direction, the scalar version. You are not breaking things into components anymore. Some students are overthinking. They will overthink this section. These are scalars. You're just finding the velocity. Nothing to combine, nothing to use the Pythagorean theorem for. It turns out, as long as there are no non-conservative forces, you can apply conservation of energy to pretty quickly find the object's maybe height or velocity or mass, depending on what information you're given. The last little part about this problem I want to say is that technically in this little unit, this whole E section of videos, we're looking at something known as mechanical energy. We're not quite looking at, say, chemical energy or nuclear energy. Mechanical energy is the energy having to do with the motion of objects or like the location of objects because of forces like gravity or springs, which we'll get to later. So you could call this conservation of energy. Technically, it's the conservation of mechanical energy. I'm not talking about like the chemistry that's going inside the block. Okay, so this might show up on problems. This isn't meant to fool you in any way. If you see this on, say, an AP exam, it just means we're doing this. We're looking at the energies associated with motion and an object's location because of forces acting on it. Okay, so this is also known as conservation of mechanical energy. Okay, all right, that's it. That's the end of this video. Thanks for watching.